This video will briefly introduce multi-branch machine learning-assisted optimization and its application to antenna design. My talk is divided into 4 parts. Simultaneously considering the performance and the robustness of antenna design is a crucial step in electromagnetic design progress. In the last 2 decades, surrogate model-based machine learning-assisted optimization, for short MLAO, has been widely studied in antenna design. Gaussian process regression can give the predicted value and predicted uncertainties, which is widely used in MLAO. LCB pre-screening strategy is introduced to balance between exploration and exploitation. The LCB constant setting always relies on the experience of designers, which largely affects the robustness and performance of the algorithm. To solve this problem, a multi-branch machine learning-assisted optimization, for short MBMLAO, is proposed. Figure 1 is the flow diagram of the proposed MBMLAO method. We will discuss the algorithm in detail. Step 1. Initialize settings. X sub L means the low-fidelity input parameter vector sampled by Latin hypercube sampling. Step 2. Get initial database. Calculate X sub L by an low-fidelity electromagnetic simulation. Calculate X sub H by an high-fidelity electromagnetic simulation. Step 3. Train surrogate model. Use multi-fidelity Gaussian process regression learning for the relationship between the input parameters and the response. Step 4. Optimize based on the surrogate model. Use a global algorithm to optimize the surrogate model constructed in Step 3. Obtain the optimal values under M groups of different branches. Step 5. Simulate and retrain. Use the low-fidelity simulation to calculate the above M groups of input parameters. Then, retrain the surrogate model. Step 6. Repredict and validate. Repredict the M group input parameters, and select the optimal one for the high-fidelity model to verify. If the termination condition is satisfied, stop the loop. Otherwise, update the database and repeat Step 3. Just one example is shown here. More details can be found in IEEE transactions on antennas and propagation. A series-fed microstrip array antenna is used as an example. For the SBMLAO method, the searchability of LCB constant is equal to 2 is better than others. The optimization results of MBMLAO are close to the best case of SBMLAO. The selection of omega will affect the searchability. MBMLAO is more robust. At last, I will make a conclusion. The MBMLAO method has been presented to achieve a balance between exploration and exploitation in antenna design. For problems with different characteristics, different complexities, and different design specifications, the MBMLAO method maintains effectiveness while obtaining robustness.
We will introduce a novel algorithm for optimizing antennas. This work was cooperated by the SOSTEC and the UTS. The traditional methods of designing an antenna are based on some rules of thumb, parameter sweeping, and optimizations. However, those methods always suffer from time-consuming problems. The SAEs proposed recently are more efficient. In this paper, we propose a novel algorithm called SAPSO with MaxP. The proposed algorithm works with an onlet-driven mode. The algorithm starts with a section of initialization. Then, a global search part is conducted with the assistance of global RBF networks. Next, a machine learning-guided PSO updating mechanism is employed to generate offspring candidates. Finally, the proposed mixed pre-screening strategy is integrated. As shown here, this antenna is optimized by the proposed algorithm as an example. The design objective is to keep the in-band reflection coefficients below -10 dB. Results show that the proposed SAPSO with MaxP is around 3 times faster than the other algorithms. Another antenna example shown here is also optimized by the proposed algorithm. The design objective is to maximize the in-band realized gain. It's obvious that the convergence speed of the SAPSO with max P is faster than that of all the two algorithms. Better realized gain performance is also achieved. Finally, the SAPSO with max P is employed to design a sequential rotation fading network with 27 design variables. The optimized results show that good impedance matching is achieved, and the transmission coefficients are almost equal in magnitude. Also, the phase shift of 19 degrees is achieved. In conclusion, the proposed SAPSO with max P is more efficient than the other algorithms. Our future work will combine multi-fidelity circuit models to enhance the proposed algorithm further. Thank you for watching.
Hello everyone, I'm glad to introduce our work in this video. It's about prior knowledge guided deep learning enabled synthesis for broadband and large phase shift range metacells in metalens antenna. In this work, metacells are pixelated into binary matrices, where 0 stands for air and 1 stands for metal. Suppose there is a metacell represented by a 30 times 30 matrix. If we introduce pixels one by one, considering the symmetry of the metacell, the potential amount of geometry patterns is about 4 times 10 to the power of 31. It's a very huge amount of data. Prior knowledge tells us that we do not need to introduce pixels in that manner. The size of a single pixel is only 0.02 lambda. It is too small to make effects on the EM performance. In this work, we use a 1 times 5 pixel block as the geometry unit. The size of the block is 0.1 lambda. It is big enough to make effects on the EM performance. Using this method, the potential amount of data can be reduced to the level of 10 to the power of 6. Based on the prior knowledge, we can use the algorithm of conditional DC gain for a metacell synthesis. In this algorithm, there are a generator and a discriminator. These two networks compete with each other in the form of a zero-sum game. Using the proposed method, we can break the phase shift limit in metacell design. In conventional methods, the -1 dB phase shift range of a triple-layer metacell is derived at 308 degrees. In this work, the phase shift range is improved to 330 degrees. Moreover, in the DL-enabled metacell, the transmission responses at off-center frequencies can be taken into consideration. This figure shows the comparison between the DL-enabled metacells and the conventional Jerusalem cross metacells. The DL-enabled metacells achieve smaller phase errors at off-center frequencies. This comparison figure shows the simulated gain of two metalens antennas designed by the JC and the DL metacells respectively. At the off-center frequencies 13 GHz, the gain of the DL-enabled metalens antenna is 2.9 dB higher than the JC metalens antenna. 1 dB and 3 dB gain bandwidth improve by 52% and 42% respectively. Table 1 shows a comparison between the proposed metalens antenna and previous works. The gain bandwidth of the proposed antenna is outstanding. Thank you for watching.